Yes. Hello, student. We were discussing Neet Test Paper 1, and we shall continue our discussion with the question number 158. The decreasing order of reactivity towards dehydrohalogenation E1 reaction of the following compounds is. So, E1 reaction, they have mentioned E1 reaction. That means here we'll be observing two steps. The first step is the formation of carbocation, right? A carbocation. In the next step, your base will be abstracting hydrogen. Right? So, for this particular question, we need to know that which of the following will yield a stable carbocation? Because an even reactions reactivity increases. Any alkyl halide, those alkyl halides reactivity towards E1 reaction increases if the carbocation producing from these alkyl halides are stable. Okay. So now, due to that reason, we have to look into the stability of the carbocation that is being formed. Okay. Now, if I remove this halogen, the very first step in your E1 reaction is removal of the halogen, right? Elimination of your chlorine or sorry, any halogen atom. So you'll be ending up with a primary carbocation over here. Primary. So if I eliminate this chlorine, I'll be getting secondary carbocation. And what about this? Or what about this? Here, I'll be getting secondary carbocation, but it's just not a simple secondary carbocation. Here it is a secondary allylic carbocation, which is more stable. It can be stabilized by the resonance, right? So coming to this option B, I will get a primary carbocation, but I have a chance of converting this into secondary allylic carbocation. So what should I do? I'll just write this over here. I can do one thing. I have an adjacent hydrogen over here. I'll just do the hydride shift. H minus hydride shift. 1, 2 hydride shift. If I do so, I'll be getting a secondary allylic carbocation. So now how to write the reactivity order? So of all these, at the very first instant when I removed chlorine, I got secondary carbocation, which is allylic. I got secondary allylic carbocation. So this should be highly reactive, right? Since we know that allylic is more reactive. So D should come first. Then after this, B should be the next. Because even though it was primary, after the arrangement, I'm getting a secondary. So I'll be writing B next. The remaining is C and A. Between C and A, C is secondary. So I'll write C. And after that, I'll be taking A, which is whose reactivity is very less when compared to all this, because it is a primary it will be yielding a primary carbocation, right? It's a primary alkyl halide and it will be yielding you a primary carbocation. So the option is DBCA. Next question. An assertion and a reason are given below. Choose the correct answer from the following options. Okay, the assertion is vinyl halides do not undergo nucleophilic substitution easily. Yes, a true statement. Just now we have discussed this, right? So vinyl halide is this halogen group bonded to carbon-carbon double bond. So this is your vinyl halide. So here I cannot have a nucleophilic substitution very easily because if I remove this halogen, I'll be ending up with the vinyl carbocation, which is highly unstable. So that's why vinyl halides does not undergo nucleophilic substitution very easily. Now, reason is even though the intermediate carbocation is stabilized by loosely held pi electron, the cleavage is difficult because of strong bonding. This statement is a wrong statement. The intermediate carbocation, whatever that we'll be getting, cannot be stabilized by your loosely, right? Obviously, it cannot be stabilized by your loosely held pi. So this is a wrong statement. Option B is a correct. Which of the following potential energy diagrams represent the SN1 reaction? So in SN1 reaction, we have two steps. First step is the formation of carbocation. And in the next step, the nucleophile will attack your carbocation to give a product, right? It goes via two-step. It's a two-step mechanism. Now, the right answer for this question is this. This is a graph which represents your SN1 reaction clearly. So here if you observe, starting point is the point where the reactant lies. Okay. Now, the energy of the system is increasing because at this point, and you can observe that at this point, the energy is at peak. The peak represent your reactant bonded to leaving group partially. That means we are breaking this carbon and the halogen or whatever the group that you'll be having. We're breaking this leaving group and carbon bond. So now carbon is happy bonded to all the four groups. Now if you are trying to break this bond and if you're trying to convert it to an electron deficient species, it is not happy obviously, right? That's why to make this happen, you have to supply more amount of energy. That means more energy is needed. The activation energy to this particular reaction is very high. So that's why the energy is increasing. The potential energy is increasing, right? So at this point, the potential energy is maximum. Okay. After this, the leaving group departs and you'll be ending up with a carbocation. Okay. This carbocation takes this point or position in this graph. This carbocation is the intermediate that is formed, which would be stabilized by the alkyl groups which is surrounding it. Okay. By inductive effect or hyperconjugation effect. Now, this intermediate can be isolated. Now, in this next step, the energy increases a bit and you'll observe a peak over here which represent the attack of nucleophile to the carbocation. Okay, this transition state. So this represent one of the transition state and this represent the other transition state 2. And after that, we'll be ending up with a product whose energy is very less when compared to a reactant, right? So always the product's energy would be less when compared to the reactant. So this has to be the proper depiction of SN1 reaction. Next, coming to 161 question number. So they've taken this alkyl bromide, actually dibromide, and they have added alcoholic KOH and NaNH2 in liquid ammonia. So both will act as a base, right? So we are adding a base to an alkyl bromide. That means here we'll be observing dehydrohalogenation elimination reaction, right? So it's also a very easy question. CH3, CH2, CH, Br, CH2, Br. Now I'll be adding alcoholic KOH. So I'll be eliminating one of the bromine and one of the hydrogen, okay? I am removing bromine from this carbon and I'm removing hydrogen from this carbon, not from this. Obviously, in dehydrohalogenation, we will be removing hydrogen from a beta carbon atom. So we'll be removing beta hydrogen. So, but I'm specifically removing hydrogen from this carbon atom because as mentioned in earlier question, this hydrogen will be more acidic because of the electron withdrawing effect of this bromine, which is attached to this carbon, to which this hydrogen is attached, right? So that's why I'll be removing this hydrogen. So I'll get CH3, CH2, CH, double bond, CH2, Br, right? So I've got this thing. Next, again, I'm adding Na, NH2, in liquid ammonia. So again, dehydrohalogenation takes place. I'll remove this bromine and I'll remove this hydrogen, right? So I'll get CH3, CH2, C, triple bond, C, H, right? Okay. Here I did not remove this hydrogen. Look, here I'll be removing first, in the first step, I'll be removing this bromine and this hydrogen, right? But in this product, I did not mention this. So if I remove this hydrogen, I'll be getting CH, not CH2. Again, in the second step, I'm removing this bromine and this adjacent hydrogen. Okay. So I'll be ending up with C, triple bond C, CH. So this has to be your product. So option D. Okay. Next, coming to question number 162nd, they have given you a mind and they've given you bromine water. This represents bromine water. So whenever you're adding bromine water to your aniline or phenol, so you'll be getting a tribromo substituted product, right? So now if I take this aniline, if I'm adding bromine water, I'll get tribromo aniline. Bromine substituted at 2 ortho and 1 para position. So now this is the X. Now to this, I'm adding NaNO2 and HCl. So this is clearly the reaction wherein we will be preparing benzene diazonium chloride, right? So you'll get N2Cl in the place of NH2, and these three bromine will remain intact. So what's in the next step? In the next step, they are adding HbF3. It's generally HbF4. The particular reaction would be Ball-Schiemann reaction, right? If you have if you are taking copper chloride or copper bromide, it would be your Sandmeyer reaction. But since I'm taking HbF4 and I'm heating this, this is a simple Ball-Schiemann reaction. Wherein there will be simple substitution of fluorine to your aromatic ring, right? This nitrogen N2 will move out as nitrogen gas and you'll be getting BF3. And the other F out of BF4, one fluorine will be substituted here and other three will be coming out as BF3. Okay, so we'll be getting this. This should be your product. So which option can you say this? So it has to be your option A, right? Yes. Coming to question number 163. They have given you this particular substrate wherein CCl3 is attached to a aromatic ring. So CCl3 acts as an electron withdrawing group. So generally, if you have methyl group, it can act an electron donating group. Now, I have substituted 3 hydrogen by 3 chlorine. Okay, this is your CCl3. Now, chlorine is electronegative. it will withdraw electron. So if this group is attached to your benzene ring, it will withdraw the electron. It can act as electron withdrawing group. So now, if you remember, electron donating group generally activates the ring and directs the incoming electrophile towards ortho and para position, and electron withdrawing group directs the electrophile towards the meta position, right? So now if I have an electron withdrawing group attached to my benzene ring, so it will direct the incoming electrophile to the meta position. So in this Br2 and Fe means you can take any iron catalyst, FeBr3, and if I'm adding Br2, so I'll be getting this iron will take one Br, I mean Br, bromine, I can write this as Br bonded to another Br, another bromine. So you will be getting this Br minus will be taken by FeBr3. So you'll be getting Br plus. This can act as an electrophile, and now this electrophile will be attacking to your benzene ring. But where will it attack? At the meta position, because I have a electron withdrawing group already present in the benzene ring. So it will attack the meta position. It can attack both the meta position, but here they have mentioned specifically that they are taking one equivalent of bromine in Fe. So that's why you have to place bromine in only one of the position. So it has to be this. Okay, this is your correct answer. Now, 164th question. Consider the following reaction. So they've given this reaction. And you can observe here bromine radical, right? Br radical. So, and you're getting an HBr in the product as a one of the product. So, clearly this is your free radical halogenation. Okay. Now they have given you the major product wherein they have mentioned the free radical that is being produced. You just have to look into the option wherever where you'll be getting most stable free radical, right? So observe. This is a primary free radical. This is a secondary free radical. This D represent deuterium, nothing else. Deuterium. Deuterium is a isotope of hydrogen. You can just imagine this D as another hydrogen. There's nothing much of a difference over here. Okay. Now, what is this? This particular radical is a tertiary radical, and this is again a secondary radical. And of all these, the B option is the correct option because it has a tertiary free radical in this. Okay. Coming to question number 165, ethylidene dichloride can be prepared by the addition of hydrogen fluoride on. So now you have to look into the option from which you'll be getting a product ethylidene dichloride from one of these reactants. Okay, so the correct option to this is this C2H2, your ethine. Look, C2H2. This is your ethine, isn't it? Now, if I add HCl to this, obviously this is an electrophilic addition reaction, your Markovnikov's addition. So here since this is a symmetrical alkyne, I can add H and Cl to any of the carbon atom. So I'll just add hydrogen to this, double bond, CH, Cl. Okay, I can take this as negative, positive, and I'll be adding this positive and negative to the either carbon. So again, I'll be adding hydrogen chloride to this. So now, according to Markovnikov's addition, the negative part of the adding molecule will be adding to the carbon atom containing least number of hydrogen atoms. So your Cl will be adding to this carbon. So you'll be getting CH3 single bond CH, Cl and Cl. Your Cl is adding, your chlorine is adding to this carbon atom because this is having less number of hydrogen atom, and your hydrogen will be adding to this carbon, and the double bond in the process will be broken, right? So you'll be ending up with this product. We needed this only, right? This has to be your product. Yes. So option C is the correct option. Okay, so now we have discussed all the questions which are based on this concept, that is haloalkanes and haloarenes. Hope you understood. Thank you, students.